Thank you guys for attending. And my name is Simon, and I'm a staff engineer at Samsung in the global open source team. And if you haven't heard about that, I can briefly say what we do there is sort of develop new and contribute to existing open source ecosystems. And that's also what this talk here today is about. Some of the new ecosystems surrounding xNVMe and the existing work that has been done on IOUing and NVMe Passthrough on the Linux kernel in the context of SPDK. So this presentation, some of the work was presented previously some 10 months ago at the SPDK virtual forum, where Jim Harris gave the introduction on how and why SPDK started, as well as SPDK's motivation. So I'll try and paraphrase what he said and give that introduction, where afterwards I'll dive into the Linux storage abstractions, telling you how and why they fail and what we can do about it. And since xNVMe is sort of the new kid on the block, I'll give you a brief introduction to that, and then dive into the performance characterizations of this new solution and how that works together with SPDK, and guide you through the next steps of what we're working on in this area. So to begin with, SPDK started a decade ago, so back in 2013. And what I heard Jim say is that he was meeting with these enterprise storage customers and their developers and saying they had a bunch of SAS SSDs in their systems, but they just couldn't get the performance out of them. And around that time, NVMe was getting ratified. It was not quite there on the shelf, but what he could see, not just on the horizon, but right around the corner, was that with these new drives from NVMe, these storage challenges that they were having were only going to get worse. And he was seeing that, it was right around the corner. OS support was ramping up quickly. We had support in Linux with the NVMe driver. And at the time, Jim was also working on FreeBSD and the NVMe driver for FreeBSD. What also happened was that the Intel storage group got merged with the division responsible for DPDK. And DPDK was tackling the same issue or problem, but for network packet processing. And the issue here was the storage abstractions or the storage stack was becoming the bottleneck for having efficient storage systems. And it seemed like it was only gonna get worse. So that motivated the start of SPDK, where the main motivation was breaking that software bottleneck for high performance storage workloads. And beyond that, to build a new open source ecosystem where people could collaborate and innovate on making new storage platforms and storage products, and sort of try and strike a balance between developing new and contributing to existing systems. So I'll get back to what I mean about that. And a key thing of SPDK is providing a broad set of abstractions and implementations for those abstractions. So looking at SPDK and NVMe, and in terms of breaking that software bottleneck, today it's still the main motivation that performance and efficiency for NVMe is priority number one. But in terms of building open source ecosystem, what we're looking at today here is some of that collaboration on integrating with xNVMe, as well as collaborating closely with new features of the Linux kernel. So sort of instead of focusing on what's provided from the SPDK NVMe driver, taking a look at what if instead of using that, we try to contribute to the Linux kernel in a way that we could leverage NVMe efficiently, and still supporting these multiple abstractions and implementations of them when developing SPDK. So what we'll be going through is an initial sort of why, taking a look at why we needed the SPDK NVMe driver. How was it the Linux operating system failed to provide what we needed, and jumping into the solution to these problems. So the stuff I'll be mentioning, we actually have upstream solutions for today, but I'll be going through it to tell you like what was the motivation behind it, what are the solutions that has been put into place today. And for that, we have these generic device handles. We have IOUing with the new command infrastructure or facility. And then we got that integrated into into SPDK through xNVMe with this thing called the BDEV xNVMe. And that's what we'll be looking at a performance comparison on, looking at our IOUing command, how that stacks up, and how this stuff behaves compared to the current SPDK implementations. So starting off with the general storage abstractions. So for many, many years, 30 years, and in my world that started out like with the Commodore 64, the dominant abstractions, and still today, are the terms of speaking files and speaking block devices. That's how a lot of people think about storing and retrieving data. So these have been the dominant abstractions and long-lived, such that in userland, what you think about is files and block devices. And that's the job for the operating system, to encapsulate this in file system abstractions and in the block abstraction layer. And then the thing where we start to speak NVMe, well, that's a responsibility of the kernel driver to do the specifics of mapping these abstractions down to a specific hardware platform such as NVMe. So how does that fail? Well, we can speak NVMe from userland through an ioctl, but that has sort of a couple of limitations. And the real failure here is sort of that we have to do it. These abstractions, we cannot make proper use of what these devices can do. So I looked in the program for SDC, so to give a couple of examples of where we really need SPDK. I think Matthias will be presenting in a couple of days or tomorrow about the large-scale deployments of CNS. And there is on the abstract dimension of CSOL, the cloud storage abstraction layer. And that thing relies, as an SPDK application, on being able to send read and writes using another LBA format where you control the metadata portion of your command. So that's an essential type of way of speaking NVMe directly with your storage device that cannot be facilitated by the kernel through the regular file and block abstractions. There are a bunch of other examples, such as the directives needed for FTP and writing optimizations such as write zeros. And you can always argue, well, that'll be the responsibility of the kernel to make use of a feature such as write zeros or device-side copy to make this stuff work faster. But there are just scenarios where you really want to move this out of the responsibility of the kernel and up into your application layer for stuff like, the cloud storage abstraction layer or distributed file systems and other ways of managing these concerns at a higher level. And especially for stuff where it doesn't fit at all, such as KV stores and now for computational storage. So the failure of these are basically that we have to bypass them, and when doing so, we also bypass the facilities and the infrastructure provided for the kernel or by the kernel to develop storage applications. So that's something we need a solution to. Another issue is that we've had is that NVMe devices pop up as controllers as dev NVMe 0 and NVMe 0 N1. However, that was only for NVMe devices with NVM and CNS command sets. If you plugged in a device, say a computational storage device or a KV device, you wouldn't get a handle to the NVM namespace. You could get a controller handle, but you couldn't do the stuff that you're supposed to of speaking with the device. You didn't have a communication channel. So that's another abstraction failure there. You can't even get that communication channel up and running. Now, then in terms of performance with Linux today, we've had IOUring, and it's been around for a while. And with that, we got very efficient traditional storage I/O. We can do reads and writes with the abstractions of files and blocks. And IOUring goes beyond just storage. It's a generic interface for communication from user space and kernel space that can be used for a bunch of things, among it storage. And there are optimizations that allow us to enable polling and trading CPU resources for lower latencies and higher IOP rates. However, the challenge of everything that we can do with IOUring is that only worked as long as we were within the abstractions of the kernel. So if you wanted to do any of that stuff that's outside of the file system and block abstractions, well, then we can't use this infrastructure. So what we have instead is just this ioctl. And the issue with that is, if you look at efficiency, if here, let's say, we have IOUring with IO depth and IOPS on the y-axis, where we have a nice scalable performance. When we increase the IO depth, we get increased IOP rates out of IOUring. When we send our commands through the ioctl, it's just a flat line, nothing happens. When we increase the IO depth, well, we're waiting for that blocking call to finish. We can then try and fix that with a thread pool. But as you see here on the yellow line, that just means that we have to pay the cost of actually setting up a thread pool. It will scale, but we have paying a bunch of resources for this type of scalability. So the downside of that current infrastructure of the driver iOctal is that it's not an efficient way of speaking NVMe from user space. So that's another thing that we need. We need to speak NVMe efficiently. Now, the existing solution to this problem has been SPDK, and basically saying, let's move the entire storage abstraction out of the kernel and into user land, and then rebuild our abstractions, such as the block device abstraction, and back it by the NVMe, SPDK NVMe driver. But let's just take a look at when this fails. And that's typically in the area of deployment environments. So one challenge is that when using the SPDK NVMe driver, we detach the kernel NVMe driver to reattach it to the infra of VFIO, PCIe, or UIO generic. And then we run that driver in user space. That can fail, or you become dependent on your hardware. Stuff can happen, such as other devices being in your same IO-MMU group. You might have a network card, a graphics card, something else that prevents you from actually detaching your device on your server. Or it might be that your hardware has an unsupported IO-MMU or a different kind of PCIe address, bar address space. That'll also prevent you from actually making use of this. And in the cloud, there might just be a sheer lack of NVMe devices, or you might just really want to be more restricted in what you can do. So this requires a sort of a high level of control of the box that you're deploying stuff on. So why this IOUring command for SPDK? Well, the thing is, what do you do when those deployment environments fail for your SPDK application? Well, you fall back to being operating system managed. So that means your SPDK application with those rich abstractions that they provide, such as the BDEV, the blob stores, and the blobfs. So all of those abstractions provided by SPDK can still be backed by something else. And that something else are typically BDEV AIO or BDEV URing. And by doing so, we can deploy some of these SPDK applications in places that are otherwise not available. But the challenge is that these things cannot speak NVMe. So doing the things such as annotating your I/O or controlling your metadata and doing these things that you need to do, they are sort of not there. But this brings us to the point that at this stage, the goals of Linux and SPDK start to align. So we want to use Linux to do all of this, such that we can enable the deployment of SPDK in places where the SPDK NVMe driver is not available. And so the main goals for Linux become that we really want an open-ended representation of NVMe drive. So regardless of those NVMe drives, whether they are NVM command sets, CNS command sets, KV stores, or computational storage, we should be able to communicate them and get a handle. And we want to be able to communicate them in a way that speaks NVMe natively, so by bypassing the file system abstractions and bypassing the block device abstraction. We want to do so efficiently as IOUring, and hopefully be able to scale as efficiently as the SPDK NVMe driver. So let's look at the solution that has been put into place for that. So for the handles, we now have this thing called the generic char device called dev ng0 and 1. It's a char device that'll pop up, and initial support was added in Linux 5.13, where it came up for NVM and CNS command sets. Later, for command set independence, this was added in Linux 6.0, where we get these handles regardless of the command set supported by the namespace represented here. So that sort of checks up the first box. Now we can talk with our devices. Then we get to the IOUring part. So the regular IOUring had opcode for reading and writing, but we had the issue of not being able to speak natively and submit NVMe commands. Then this facility was added to the kernel called the IOUring command. And that's a generic facility where you can attach IOUring capabilities to a command provider. So, and that sort of means that you can do stuff, and one requirement I should mention is that larger ring entries allows you to embed commands. So this fits very well with NVMe, where the IOU ring submission queue entries and completion queue entries could map directly to the NVMe submission queue and completion queue entries. And that can then be implemented as a command provider, either in a driver or a file system, or a different kind of subsystem in the kernel. So specifically, we have this provider in the NVMe driver, where we're providing NVMe Passthrough commands. And the way you define the commands are the same as what you do if you're using the NVMe driver ioctl. And it sort of leverages that facility in the kernel. So around this time, we also got added the support for IOVEX. So this was sort of, we were working on getting this stuff to work for, in the case for SPDK, and SPDK's BDEV abstraction relies heavily on the IOVEX support. So we sort of got that to work along with that as well. So at this point, we got everything I think that we needed. We can bring up the devices with the handles. We can speak NVMe natively, either through the ioctl or through the IOU ring command infrastructure. And the question is then, does this scale as efficiently as IOU ring? Like when we're embedding these NVMe commands, does that work as well when just doing regular IOU ring? And for more details on this, then I would invite you to look at my colleague Kanchan's work on this. He presented some of this at the Linux Plumbers Conference last year. So for some of those details, please have a look at that. So how does this then integrate with SPDK? Well, that happens through xNVMe and something called BDEV xNVMe. So to dive into this, I need to briefly introduce what is xNVMe. And the essence of xNVMe is that it allows you to think about commands and submit them in a blocking and a non-blocking manner. So I'm saying blocking and non-blocking because if I say synchronous and asynchronous, it's very hard to hear the difference when I pronounce it. So I'm just going to say blocking and non-blocking. And what I mean by here in blocking is that you construct the command. So if you're used to IOU ring, you say you prep a command and then you submit it. So here in xNVMe, you'll prep your command and send it in a blocking fashion, wait for it to complete, and then it comes back up again. So your thread is blocked. And in the non-blocking manner, you prep your command, you submit it, and then your thread can go and do something else. Then when you're ready to receive the result, then it goes through a queue where a callback function is invoked. So that's sort of the infrastructure that's provided by xNVMe, is that you don't have to think about anything else than commands, the payloads for your commands, and whether you want to send them in a blocking or a non-blocking manner. What you can then do is that xNVMe is backed by a bunch of implementations. So that's for regular I/O and POSIX I/O, as libaio. There are thread pools, there are the NVMe ioctls, and IOU ring, and something in the next presentation on this track, which is libvfn, which is another userspace NVMe driver, and of course now with IOU ring command. And that's just for Linux. There's support for FreeBSD in Windows as well, where we have interfaces such as IOCP and Microsoft's version of IOU ring called IO ring on Windows. And on FreeBSD, we also have the SPDK NVMe driver. So in general, just a bunch of implementations. And the point here is that when you implement these things and you need to access and speak NVMe natively, you don't really want to think about all of these different ways that you could actually do that. So you can just think about your command, express that, and send it down into the operating system. Then building on top of this, you have a bunch of command set helpers. So that is to do the prepping of commands, whether that's NVM reads and writes, CNS zone management, or KV stores, or computational storage. And there's also a small suite of command line tools. So in this area, it's also worth mentioning that we're trying to, in an upstream manner, to collaborate with the NVMe CLI command line tool to see how we could integrate the library behind xNVMe such that NVMe CLI could make use of all of these different ways of talking with storage devices. So xNVMe is generally used for this I/O interface independence. So that's also how it's being integrated into SPDK to take care of how this stuff is submitted for the BDEV layer for the different kinds of interfaces available by the operating system. What we aim for is always a minimal abstraction cost, since in the world of performance, and especially on SPDK, this would really not have any adoption if you were paying a bunch of cycles on the abstraction layer itself. And for more details, I would invite you to look at this paper that was presented last year at SysTor, and have a look at the webpage as well. So that brings us to the final component. So we now have the handles for the uring command and the char devices. We have the uring command infrastructure, and we have xNVMe as a way of thinking about commands and submitting them using that infrastructure. And to tie that into SPDK, well, that happened with the SPDK version 2209 and the introduction of BDEV xNVMe. And what's illustrated here is basically just that with a single BDEV of xNVMe, you get access to libaio, iouring, and iouring command as a replacement or potential replacement for the current BDEVs in SPDK that are called BDEV AIO and BDEV uring. And for details on this, my colleague Krishna Reddy presented this at SDC earlier. Great. So with all of that in place, we get to take a look at, so how does this then perform? Both the raw benchmarks on peak IOPS for saturated CPU. So we want to look at a saturated CPU to see how many IOPS we can squeeze out of a system on a single physical core, as that's the best expression of how efficient is a given interface. And we'll be looking at iouring command, as well as iouring and iouring command versus the SPDK NVMe driver. And then we'll look at the implementation or the integration of this into SPDK. And the system that we're using here is sort of a workstation setup with SMT enabled and Turbo Boost disabled, with 8 devices in it that peaks out at around 8 million. And the software is provided here for reference. And what's worth noting is that to get the optimal performance out of iouring, there are a couple of kernel tweaks that you need to apply. They are provided here for reference. And what's quite essential is that you enable poll queues on your NVMe driver. So if you want to reproduce these numbers, this is worth taking a look at. And initially, we're going to look at this thing from FIO called test iouring, which is a test specifically made to see how much IOPS that are possible to tweak out of the iouring interface. And for the same for SPDK, we'll be looking at the BDEV perf tool that's provided with SPDK. And for reproduction of this, then there's a GitHub repository where all of the numbers we've extracted are available, and all of the information needed for you to reproduce this. All right, so what do we have here? So initially, what we're going to look at is the number of devices. We have 8 in the system, and then 4 different configurations for running test iouring. So why am I doing this? Well, that's to get a sense of like what's required to get efficient use of iouring. And what we've done here are 2 configurations with IO polling enabled, one with SQ polling enabled, and then one without any of these polling modes enabled at all. And what you see here is that if you don't use polling, you're not going to get any more than 1.39 million IOPS out of your system. Polling is essential to get scalable performance out of this interface. And if you try and say, I'm just going to, on the one physical core, I'm going to dedicate or create a thread per device, that doesn't really scale either. You hit a boundary already here at 2 devices. So this seems like the best configuration for iouring. That's what you see here. And that is to have one thread to map to one symmetrical hardware thread. And then make sure that you use batching and enable IO polling, and then tweak your batch sizes. And by doing so, the best effort we get here is 4.16 million IOPS. So that's sort of the best effort that we get out of iouring on this system. So let's have a look at iouring command, how that stacks up to this. And we're basically looking at the same numbers. However, what we see here is that we do get better scalability. So instead of 4.16, we have 4.86 million IOPS. So with that, as an evaluation of the goals for Linux on how we can do these things differently using the existing infrastructure and contributing to the Linux open ecosystem, well, we got the devices, we can speak natively, and we can do so as efficiently as IOUring. There's actually even a small benefit of going through the IOUring command infrastructure. So the last question here is then, how does this scale as efficiently as the SPDK NVMe driver? And for that, we did the synthetic benchmarks with the BDEV perf tool with 2 variations, also a single physical core and no thread sibling, and then another one with a thread sibling. So that was to get the equivalent SMT effect that was done with the test IOUring. And what we see here is that with SPDK, we actually get 7.24 million IOPS. And using the thread sibling as well, then we're no longer congested on the CPU. We've actually maxed out the devices on the system. So why do we have this gap from IOUring command and up to the SPDK NVMe driver? Well, I think what we're starting to see here is that we're paying the cost of constants. So scalability is actually fine. But even here in this example, we are doing less instructions on the I/O path. We are by using the generic char device handle and bypassing the block layers, well, there's just less code that gets executed. And specifically for SPDK, there's even less general infrastructure to take care of, so it just has less work to do on the I/O path. So by stripping off that, you get these higher rates. But we've gone from a world where we were stuck at around 1 million IOPS in a system like this, and now we're at 4.8 million. So you would say that the Linux kernel infrastructure is sort of closing this gap rather rapidly to what can be achieved with the userspace NVMe driver. And there are still untapped optimizations, specifically with regards to the DMA mapping of the buffers for the commands that are executed in these kinds of tests. So yeah, we're almost there, but we're not quite there on this scale as efficiently as the SPDK NVMe driver. So let's go next and see how this is integrated into SPDK, and we'll be comparing the different BDEV implementations with the BDEV xNVMe implementation. And the first thing to notice here is that for 1 device and for 8 devices, and there's really not much to see here, it's basically the exact same thing. But I'm presenting this because, as I mentioned, some of this work has been done prior, 10 months ago, and there we had other issues, and we were not hitting the same scalability as we are today. So I'm very happy to be able to set that checkbox there. And then comparing now BDEV uring with BDEV xNVMe. Here we have 3 configurations. And what you see over here, we have with 1 device and 8 devices, the I/O depth on the x-axis and IOPS on the y-axis. So for BDEV uring, that's this purple line, light purple. That's hidden somewhere down here. And on top of it, there's another BDEV xNVMe. And this thing is called conserve CPU. And the difference between these 2 things or there are basically no difference on the BDEV uring compared to BDEV xNVMe when it's trying to conserve CPU. And the thing that's hidden behind that flag is that what we have up here is that these 2 implementations don't use I/O polling. And the BDEV uring in SPDK doesn't have support for the I/O poll feature. But what you can do with BDEV xNVMe is that you can flip on I/O polling, and then you go from the graphs you see here and bounce up to this one. And same here at 8 devices, we just see that graph scaling up better. So the good news here is that if you're running an SPDK application and you're falling back to using BDEV uring, well, you have a performance boost to gain there just by using the BDEV xNVMe at this point. Now, let's take a look at how BDEV uring compares for uring command. So what we're looking at here is 1 device in both cases. These are the uring numbers and these are the uring command numbers. And what you see is that we're just doing slightly better, both in the case of conserving CPU and not conserving CPU, so using I/O polling. So that's great, we can tick off those boxes, and the story is the same for running on multiple devices. So a lot of check boxes all the way around. And just to say that 10 months ago, that was not the case. So if you go back and see what we presented at the SPDK virtual forum, then the numbers weren't as great as they are here. So it's just saying that their work has gone into this, and I think we're in a pretty good place of integrating the IO-Uring command infrastructure into SPDK. So what are the next steps? And one thing that we really want for Linux is that we have the IO access control for these device handles with the ability to disable capsus admin. And actually that has already been done. So now you can do stuff such as sending these identify namespace, identify controller and such. And why is that interesting? Well, that's interesting because when you only have the handle for the generic char device, you don't have the infrastructure of userspace on a block device that can tell you stuff like what's my block sizes or what's my IO sizes. All of that stuff is gone. So you need another way to communicate with your device to know about capabilities and what it can do. And that you can do by sending these identify commands to the device. Yeah, and then what needs to be done more is investigate the further potentials for larger block sizes and see if we can do some optimizations on the Linux kernel's DMA infrastructure. And for BDEV xNVMe, well, we really wanted to look at efficiency such that BDEV xNVMe could match what was there in SPDK for BDEV IO, AIO, and Uring. But that stuff has actually also been fixed now. And in the case now where we can enable IO polling, we can actually exceed the performance of what was there prior. Now, there's also some potential stuff we can do now. Since BDEV xNVMe provides ways to speak natively, it provides a way to do stuff such as managing your metadata, doing all of these things that otherwise require the SPDK NVMe driver. And there are different SPDK applications that can then benefit from that. There's even the sort of perhaps crazy thing of deploying SPDK applications on Windows, since with xNVMe you get support for IOCP and the Windows IO ring. So in general, there'll just be a broader deployment of SPDK applications using BDEV xNVMe. Now on xNVMe itself, there are some stuff that are currently supported with different optimizations that we can do on IO-Uring. And especially for batching, that was some of the stuff that has helped reach us the performance goals that we had. We still have some stuff and some room for optimization with regards to resource registrations and different ways of controlling the IO polling infrastructure. And there are some other general optimizations. So there's still room there. So yeah, by the end of this, what does this mean for SPDK? Well, the BDEV provided by xNVMe sort of shows that it can encapsulate the challenges and the use of the general Linux infrastructure. So that means potentially there can just be a single BDEV implementation making efficient use of the Linux interfaces through IO-Uring and IO-Uring command. For the SPDK NVMe driver, well, it's still the most efficient way of shipping your IO to your devices. So you should probably just see it as the benchmark of how we can optimize the Linux kernel to get the most out of it. Well, the SPDK NVMe driver is what we can use as the roofline. That's the goal we need to reach. So I think that brings me to the end. And with that, I just want to say, if you want to see the previous presentation on this, there's a link for that there. And if you want to collaborate on some of this work that we're doing, then we're hanging out in the SPDK Slack channels. We also have a Discord for the Samsung Global Open Source team. So if you're interested in the IO-Uring command infrastructure for Linux, the SPDK block devices, or xNVMe, please come and talk to us and tell us what you want to discuss. So I think with that, any questions? Yeah.
Will this work with zone namespace devices that do not support the zone depend command?
Great question. So the question was, will this work with devices? Oh, can you repeat it?
That do not support the zone depend command.
that does not support the zone append command? And the answer to that is yes, it will. So the neat thing about the generic char device handle is that it'll bring up any NVMe device, regardless of whether the Linux kernel has a matching device model for it. So there are certain CNS configurations that doesn't match the Linux zone block device model. So when that match fails, you can still communicate directly with the device using this IURIN command infrastructure through the handles provided through the NVMe generic char device.
And as background for those who don't know, when we developed the CNS command set specification, we knew there were a lot of use cases that absolutely could not use zone append, where you don't know until after the command is done what logical block was written to. So we made that command optional. However, Linux, as you pointed out, requires that, otherwise it will not mount that zone namespace device. So, good, I'm glad you're working around. So I guess you don't know of any effort now to make that optional within Linux, that command? Talk to Christoph Helwig a lot.
I think there are other candidates here that knows better what the status of that is. I think there's Matthias here and Damien and Christoph, and I'm gonna stay out of that one.
You're doing a good job.
Yeah, I'm staying out of that one. Yeah.
Okay.
Oh, sorry. Yeah.
What about tracing capabilities? Is there any tracing capabilities like block trace?
Also, you're asking, what about tracing capabilities? Are there anything like block trace? Actually, don't know. No, I don't think so. So, what would that look like?
Get insight on the different activities within the stack. Yeah, I guess this is directly to the controller itself. The stack is kind of minimized.
Yeah, so one thing that is enabled on SPDK is that there's something called the SPDK top, where you basically, from the viewpoint of an SPDK application, you have all of these pollers and you have a framework for setting these up. And you can get very close insights into how these are executing and what are the latencies of each worker and what they're doing. So it's probably not going to be like block trace, but there is infra in SPDK at least for looking at that. But I think for something like if you say the generic infra on Linux for the generic char devices and whether you could do something like block trace, then no, because that part of the Linux stack is sort of bypassed when using this.
What about capability? You have like a lot of devices, right? That's the limitation, right? You have like 24 NVMe devices, and all of them are doing a lot of threads. These are, does it tap into the context switching on the Linux kernel and the structure, or is it limited by, let's say, like, you had a 24-bay server, you're limited to the 8 devices because of your CPU limitation?
So yes, what you're asking is what about scalability? What are the challenges there? And I think for what we see here with these peak I/O benchmarks is basically how much can you get out of a single physical core, and the results are like you get more out of a physical core with the user-space driver, but by using IURIN command and enable polling, you can get pretty decent results. At some point, you have maxed out what one CPU can actually do. But it does sort of scale up. But if you compare these results with, say, the numbers provided by Jens Axbo on Twitter, you'll see that they are sort of different. And the setup is a slightly different setup, where he usually has these very fast drives doing 5 million IOPS. So he has one SMT thread to saturate that. And then he scales out by saying, I'm going to spend another SMT thread to get even more IOPS, and then another core and another thread on that to get even more. But what we're doing here is saying, how much can we get out of one? And what's the boundary there? Because I think it's more relevant to see how we do efficient scale out, especially when these kinds of devices seems to be disappearing a bit, right? So about making use of more devices rather than a single one.
So is there concurrency limited at this time?
I think you're just limited by the, no, I don't think it's limited. Like, in what way would you say?
Trade-off, right? Trade-off concurrency versus because of CPU demand for this call, right? Instead of like you're kind of minimize it, but when you have like when you try to scale out, you're trying to it's kind of hard to saturate the resources of NVMe drive before you hit the CPU saturation, right? So it's like a trade-off of concurrency versus performance.
Yeah, so the experiment is set up specifically to see that we want to saturate the CPU, and then it's a question of how many IOPS can we get out of that CPU. So that's why we hit the bottleneck. Yeah.
Yeah, I'm talking more broader than.
Because so in general, I think what you will always see is that when you use IOUring or IOUring command, you have to pay the cost of crossing a boundary between user and kernel space. There's infra with IOPOL that'll reduce that cost, and you amortize it further by doing batching. So you need to do all of these things and tweak those and tweak the batch sizes such that it fits perfectly with your setup. And then you do all of this to amortize that cost that's sort of costing you cycles. And that's where the SPDK driver just has fewer boundaries that you need to cross, because you don't have that separation. So you don't need to do batching to actually get the performance that you get out of the SPDK driver.
Okay.
Yeah.
Thank you.
What's the applicability then of Fabric?
Yeah, okay, so what's the applicability to NVMe over Fabric? So that's an excellent question. So the really interesting thing is that a lot of infra in the Linux kernel is based on you exporting a block device over fabrics. But I think what we've achieved with the IOUring command stuff is that you can also just export the generic char device handles. So that means you can now have these fabrics targets for stuff that's not just NVM. So stuff that's not block, we can still use the fabric support for that. So basically, yeah, expanding the support from just block to KV and computational storage over fabrics.
Okay, and in terms of scale and initiator and target performance, you should see the same benefit on the initiator side as you're seeing for the local platform?
So the question is the performance the same, or do we see the same benefits over fabrics when using this infrastructure? And I haven't run the numbers, so I can't tell you whether we do. But I would suspect that yes, it is. But yeah, I don't have the numbers to back it up.
But that's all things that there's no reason to think you would.
Exactly. Yeah.
This is a related question to that, is how does xNVMe interact with multipassing for Fabric?
So it basically delegates that responsibility. So the question was, how does xNVMe interact with multipathing or porting for NVMe, right? And the answer is that, well, for this infra, we delegate that to the kernel. So that's however the kernel does it. And xNVMe just grabs a handle through the infra to the generic char device.
I have two questions. First one is SPDK sent for NVMe and character devices, or can be sent for both devices like SAS and
Yeah, so let me answer that first one. So did you said SPDK, is that only for NVMe devices, right?
Exactly.
Yeah, no, it's not. So it has the fallback of using these other, there's a bunch of implementation in SPDK. You can also use a memory-backed block device. There are implementations doing different kinds of parity control and using SAS. So basically in that case, it's relying on operating system managed I/O. So basically falling back to using libaio in the BDEV AIO implementation, or BDEV uring for using IO uring infra to talk with your SAS or SCSI devices. And the same thing now with using BDEV xNVMe. Then we just fall back to letting the operating system manage that and talk with the devices through libaio, IO uring command. And then the other question, yeah.
First question, is it using the same model for Linux abstractions for devices like SAN, etc.? Because, you know, this mid-layer, SCSI layer, that's derived for float devices like UPS, etc. So it's using the same concept for NVMe as well, for abstracting these layers and accessing the device directly?
I think you have to repeat that question. I don't think I quite follow that.
Okay, the concept for SPDK and abstracting the Linux, right, and these layers and accessing the NVMe device layer. It is the same concept and same layer abstraction in case of float devices as well.
So yeah, in SPDK you have the BDEV abstraction, and that will be the same, abstraction, whether you're using underneath the SPDK NVMe driver to go directly, or using IO uring command to go to the NVMe device, or if you're using libaio or IO uring to go to a SCSI, a SAS or SATA drive.
Second question is, do you have any benchmarking or performance impact numbers or comparisons for those float devices that are needed for SAS?
So I don't, but if you check the SPDK project, spdk.io, with each release, they do this massive performance report showing you all sorts of aspects of how SPDK performs in different environments. So I think definitely check that out, and then also jump on the SPDK Slack channels. It's an amazing community where you can reach out and like say, what are your experiences with using these types of hardware? Yeah. So you're asking the performance numbers I showed, was that with IOMMU on or off? So that was with the IOMMU using VFIO PCI. So I think what you're saying here is that there are challenges to using an IOMMU, that it could bottleneck your IO, right? Is that what you're saying? Yeah, so I think with SPDK, you get to do the sort of a pre-allocation of all of your mappings. And so that means on your IO path, for every IO, you have to do less work in resolving your buffers. Whereas the infra for the DMA allocations through this on the Linux kernel, that's where you might see some bottlenecks popping up. And I think there is stuff to tweak there. Yeah. And I think actually in the talk after this, there might be stuff related to this on the VFIO infra for this. All right. Any other questions? Great. I think that's it. And please catch me if you have anything you want to discuss offline. Thanks.